You have 11,000 rows and a question your manager asked casually on Tuesday: are there natural groups in here? You run the obvious tool, you get a grouping, you put it in a slide deck. 2 weeks later, a colleague runs the same tool on the same rows and gets groups that disagree with yours. And neither of you typed anything wrong. You both used the same library, the same number of groups, the same data. One of you will look careless in front of that same manager, and neither of you can say which one. How rare is that? It is not rare at all. It shows up on ordinary data, with ordinary settings, to careful people. And the cost lands somewhere real: a customer segment that shifts under your feet, your churn model retrained on groups that quietly renamed themselves, the alert threshold that moves on you for reasons nobody wrote down. You lose hours to it, and you usually lose them twice, once finding out and once explaining. So what makes two of your own runs disagree? Hold that question. We will come back to it at the very end, and the real answer will change how much you trust any grouping you have ever shipped. It is not a bug in the library, and it is not your data being messy. And you should care even if you never write the clustering code yourself. Somewhere in your product, a grouping like this already decides which customers get a cheaper plan, which alerts get raised, which documents get filed together. If those groups reshuffle on every retrain, your on-call phone finds out before your dashboard does, at 3 in the morning, and you are the one asked why. Let us make this concrete and keep it for the whole episode. Kiln is a small internal service two people run at a hardware company. Kiln has one job: sort 11,000 support tickets into groups so a human can route them, instead of reading every ticket the way you would otherwise be doing yourself. 20 numbers describe each ticket. How many groups ought there to be? Nobody knows, and nobody wants a research project that costs them a month. Ask what this method is, and the easy answer arrives instantly. It is called k-means. You say how many groups you want, and it finds them. Simple. But that is not a definition, it is a description of the buttons. What is it actually minimizing? Until you can say that out loud, every argument about whether Kiln has good groups comes down to which picture looks nicer on your slide. The quantity it minimizes has the unglamorous name and a very small shape. For every ticket, measure the distance to the center of its own group, square that distance, and add all 11,000 of those squared numbers together. 1 total. What does lower mean? Tighter groups. That is the entire objective, and notice what is missing from it: no notion of how many groups is reasonable, no notion of what shape a group should be, no notion of what any group means. So k-means is the answer to a question that sounds impressive and is narrower than it sounds. Given a fixed number of centers, place them so the total squared distance is as small as possible. That is all. Kiln does not learn what a ticket is about. Kiln learns 20 numbers per center, and every claim you make on top of that inherits exactly that much meaning and no more. Note, why squares, and not plain distances? Because squaring is what makes the ordinary average the correct center. Gauss argued this 200 years ago about measurement error. The value that minimizes the sum of squared deviations from your set of numbers is exactly their mean. Swap in plain distances and the best center becomes the median instead, which is a different algorithm with different behavior. The word mean in the name is a consequence, not a casual choice. Now the mechanism, and it is 2 steps long. Stuart Lloyd wrote it down at Bell Labs in the 1950s, and it is the code inside nearly every library you will ever call. Step 1, assign every one of your tickets to whichever center is nearest. Step 2, move every center to the mean of the tickets that just chose it. Repeat. Is that really all of it? It is, and there is something genuinely elegant about how little it contains. Watch what each step does to your score, because this is the load-bearing part. The assignment step cannot raise your total. Every ticket either keeps its center or moves to a nearer one, and nearer means a smaller squared distance. The update step cannot raise it either. By the argument in that aside, the mean is the point that minimizes squared distance to a fixed set. So your total goes down, or stays exactly where it is, every single round. It is monotonic, which is a proof that Kiln always halts. And here is where almost everybody gets quietly misled. It converges. It always converges. But converging tells you only that the total stopped going down, not that the total is small. What the process finds is a local minimum, a configuration where no single reassignment and no single center move improves anything, while a completely different arrangement of the same centers scores far better. The algorithm has no way to see that arrangement, and neither do you, because every step it can take goes uphill. Let us do the arithmetic, because the failure is easier to believe when you can count it. Suppose Kiln has two genuinely separate blobs of your tickets, 500 in each, and the blobs sit 200 units apart. Ask for two groups. If one center starts in each blob, the total is small, each ticket sits a few units from its own center. Now start both centers inside the left blob. The assignment step splits the left blob down the middle and hands the entire right blob to whichever center is marginally closer. Every one of those 500 right-hand tickets now contributes a squared distance of roughly 200 squared, which is 40,000, instead of something near 9. Can anything fix it? Nothing can. Move either center toward the right blob and it loses its own tickets first, so the total rises, so the step is never taken. That is a stable, converged, catastrophically wrong answer sitting in your deck, and the only thing that decided it was where the centers started. This is not a curiosity at the edge of the input space. David Arthur and Sergei Vassilvitskii opened their 2007 paper with a family of point sets where uniformly random starting centers give a total arbitrarily worse than the best possible. Not twice as bad. As bad as you care to make it, by sliding the points further apart. Case in point, does that mean the tool is broken? No, and this is the part that repays understanding. Everything above is a statement about the starting centers, not about the two steps. The two steps are provably fine. So the whole quality problem has been pushed into one place, which is a wonderful position to be in, because now you only have to be clever once, at the very beginning, and never again. Which is exactly what k-means plus does. Choose the first center uniformly at random from your tickets. Then, for every remaining ticket, compute the squared distance to the nearest center already chosen, and draw the next center at random with probability proportional to that squared number. Repeat until you have all your centers. How much more code is that than choosing at random? Barely any, and it spreads your starting centers out without ever hardcoding what spread out is supposed to mean. The squaring is doing the real work, so put numbers on it. Take a ticket sitting 1 unit from its nearest chosen center and a ticket sitting 10 units away. 10 is 10 times further, but squared it is 100 versus 1, so the far ticket is 100 times more likely to be picked. Double the distance and you quadruple the chance. That is why a far-away blob with no center in it almost never gets skipped. It is not merely favored, it is favored by the square of how badly it has been neglected. In practice, that changes the two-blob disaster from a coin flip into something you would struggle to reproduce on purpose. Once the first center lands anywhere in the left blob, every ticket in the right blob carries a squared weight of 40,000 against the left blob tickets carrying single digits, so the second center lands in the right blob with probability very close to 1. The failure has not been outlawed. It has been priced out. Now, what does the guarantee actually say, and what does it not say? Arthur and Vassilvitskii proved that this seeding gives you expected cost within a factor of order the logarithm of the number of groups times the best possible total. Read that slowly, because you will hear that fancy name quoted as if it had solved the problem. Expected, so any single run of yours may still be worse. Logarithm of k, so with 16 groups you are being promised a small multiple of optimal, not optimal. It is a bound, and a bound is not a result. Which is why the unglamorous defense still matters more than the clever one. Run your grouping several times from different seeds and keep the run with the lowest total. In scikit-learn the knob is called n in it, the number of independent restarts, and for years its default was 10. How much does that cost? 10 times the compute, and on a table the size of Kiln, that is seconds. If 10 runs give you the same total, you have evidence. If they give you totals spread across a range, you have just measured your own uncertainty for free, which is a far better outcome than a single confident number. Caveat, none of that helps you choose how many groups. And here the objective actively lies to you. Add a group and your total squared distance falls, always, because every center only ever has to cover a smaller neighborhood. Take it to the absurd end, give Kiln 11,000 groups and every ticket becomes its own center, at zero distance, for a perfect score of nothing. So the objective, asked how many groups there should be, answers as many as you have rows. It is a monotonic function pretending to be a judgment. The folklore fix is the elbow, plot the total against the number of groups and look for the bend. It is received wisdom, it is genuinely useful, and it is also not a criterion, it is a person squinting at a curve. Two competent people find the bend in different places on the same plot, which is how Kiln ends up in your deck with 5 groups and in a colleague's with 8. If the choice matters to a decision you own, the number has to come from outside the algorithm, from what your routing team can actually staff, from a labeled sample you check by hand, from the cost of being wrong in each direction. Here is the part that will surprise you once you have fixed your initialization, and it should be the thing you remember. Perfect seating does not repair the shape assumption. Assigning every ticket to its nearest center carves your space into straight-sided cells, the Voronoi cells around those centers. Straight, flat boundaries. So if your true structure is two long thin overlapping bands, or one dense blob beside one sparse sprawling one, no starting configuration recovers it for you, because the answer you want is not expressible in the language the objective speaks. Case in point, the iris measurements that Fisher published in 1936, 150 flowers, for measurements each, 3 species. It is the most clustered data set in history. So does k-means recover the 3 species? It does not. It routinely merges 2 of them, because those 2 overlap and are not equally sized round blobs. The algorithm is not failing you there. It is answering the question it was asked, which was never which species is this. In practice, one more thing bites harder than either of those, and it is invisible in the output. The distance is a sum over your 20 features, so the feature with the widest numeric range dominates every assignment. If one of Kiln's 20 numbers is a byte count in the millions and another is a flag between 0 and 1, the byte count is the only feature that exists. Your groups will be a rescaled histogram of that one column. Is standardizing the columns a pre-processing chore? It is not. It is you deciding what distance means, and if you skip it, the decision still gets made, just not by you. There is something perverse worth enjoying in all of this, and it explains most of the disappointment you will feel. You reach for this method to discover whether structure exists, and it cannot answer that question at all. Hand it pure uniform noise, ask for 3 groups, and it hands you back 3 tight confident groups with a respectable total, every time. What in the objective could say no? Nothing can. So the tool you reach for to find out whether there are natural groups always reports yes, which is very nearly the opposite of what you wanted from it. So how would you know if any of this applies to your own grouping? Do not take my word for it. Run the experiment, it takes about 10 minutes. Fit your grouping 5 times with 5 different random seeds, and each time record 2 things, the final total, and the labels. Then compare. If initialization were not deciding your answer, the 5 totals would be nearly identical and the labels would agree up to renaming. Measure how many rows change group between run 1 and run 5. That single number tells you whether you have been reading a result or reading a seed. And the honest limit is worth stating plainly, because the field does not have a better answer to offer you. Finding the arrangement of centers with the genuinely lowest total is computationally hard in the worst case, and no one has a practical method that hands you a certificate saying this is the best possible for your data. Everything in your production stack, everywhere, is a good local answer with a probabilistic argument attached. As far as anyone knows, that is the state of it, which is worth saying because a bound quoted confidently sounds like a proof of quality and is not. So, back to the opening question, what made your 2 runs disagree? Not the library, not the data, and not either of you. 2 random seeds, 2 different local minima of a total that has many, and 1 algorithm whose only guarantee is that it stops. The answer is duller than a bug and much more useful, because it tells you the fix is not a code review. Your fix is a seeding strategy, a restart count, and a habit of reporting the spread rather than the single run. Which leaves the judgment with you, where it belongs. Before you next ship a grouping, ask yourself 3 things and answer them with numbers rather than with a plot. How much do my labels move across seeds? Where did my number of groups actually come from? And what did I decide my distance means when I chose my units? If you cannot answer the third one, you have not chosen your units yet. Something else chose them, and it will not be in the room when someone asks you why the groups changed.